All right, everyone, we are back and we are about to get into our phase diagram. So we see that we have, this is this line here, this is this line, this is HCP. So now this will be HCP plus BCC, BCC plus liquid. And then we can kind of go through liquid plus this, BCC plus this one plus this one, this one plus this one. This will be TIZN plus liquid in this little region right here. This will be TIZN2 plus liquid right here. This will be liquid plus TIZN2 as well. This will be this plus, and we can see here, let's see here. This is telling us that this is TIZN right here. This will be TIZN5 plus, or this one here. Basically this line plus this line plus this line, and then you can kind of see the picture here. Excellent. So I'm going to delete all these. Indicate congruent melting points. So we've got one right here. We probably have one right here, and then there's going to be one right here in the pure material, and possibly one right here as well. But again, that's kind of up to interpretation. Invariant points. Well, this looks like the bunny rabbit ears. Solid to two new solids. That's going to be a eutectoid. This is BCC, solid to a new phase solid. This is a peritectoid. Very interesting. Bunny rabbit ears here to solid. That's a eutectic. Another bunny rabbit ear to two-phase solid. That's going to be a eutectic as well. That's congruent melting point. Here, solid plus liquid to a new solid. That's going to be peritectic. Liquid plus solid to a new solid, peritectic. This is going to be a solid here. This could be a peritectoid. And solid here. So that could be another peritectoid as well. So those are your invariant points. Consider a composition of 0.55. So 0.55 mole fraction of Zn at 1200 K. Always be careful about the temperature. That's a horrible line. Let's go ahead and just try to draw this somewhat straight. All right, so here, and we could actually just draw this right here. So what are the phases that exist in this region? Well, I've got TIZN and TIZN2. Those are the two phases that exist in this two-phase region. The composition of TIZN is equal to 0.5. Composition of TIZN2 is about equals to, let's see, that's 0.7. Let's just say 0.6. It's not quite 5. Let's just say 0.68. Again, arbitrary. I mean, again, I don't care too much about this. And my initial composition is equal to 0.55. Here we go. What is the composition and fraction? So there we got the composition. So the fraction of TIZN will be equal to, I need to run the opposite. So I need to go to the other side, 0.68 minus 0.55 over 0.68 minus 0.5. Fraction of TIZN, and again, I'm closer to TIZN, so that should be the larger phase, and 2 should be smaller, and that's true because it's going to be opposite direction, 0.55, the lever rule, 0.68 minus 0.5. Excellent. Relate the chemical potentials of each phase in this region. They must be equal because we're in a two-phase region, so the chemical potential of TIZN equals chemical potential of TIZN2. And if I'm in this region, what's my Gibbs phase rule? D plus P equals C plus 1. Components is 2 plus 1 here, 2 phases, 1 degree of freedom. Because again, if I change temperature, that composition will change. If I change compositions, it basically, well, it's going to go out to here, and then your temperature line is effectively fixed as well. So if I change, a composition in here, you're going to see, well, this is a nice one, but it's that your temperature is effectively fixed. If I roll down in temperature here, then you'll see kind of a different value here. Excellent. Alrighty. Okay, draw free energy curves at this value here. So this is, we'll take a little exercise here. So, but we can do this together. So I see, if I'm trying to draw a free energy curve here, I'm going to see lines where I cross something here, I cross something here, and that's going to be very difficult to draw. A section here, and then a section here. So here I'm liquid, here I'm liquid. Or not liquid, excuse me, I'm BCC here. So I'm BCC in this phase. Here to here, I'm in a two-phase region. So I'm in BCC plus TIZN. TIZN. And I'm going to indicate, BCC is going to be red. I'm going to indicate this is blue. Actually, not going to indicate that as blue. I'm going to indicate that as green because I'm going to say blue for my liquid. All right, and let's keep moving here. So then we have TIZN in this region here, plus the new phase, which we'll do like a gray, TIZN2. And then here you have TIZN2 plus a liquid here and here. So now in the two-phase region, like there is a instantaneous moment where I'm actually here and here where I'm just a pure material, but that's very difficult to draw, so I wouldn't I wouldn't expect you to do it. If you show that detail, that's fantastic. But I'm going to draw in these two-phase regions, I'm going to draw a common tangent, just kind of a line arbitrarily. So when I draw my curves, I'm just going to go, BCC is going to touch here, and then it's just going to disappear. And then the green curve is going to come in out of nowhere because here I'm just pure BCC, so it needs to be higher. And now I'm going to touch my curve. We're in two-phase region here, and then this is going to escape as well. I mean, it doesn't matter how you escape it out there. Then I'm going to draw this guy coming in way over here. Again, it's always less. It touches the two-phase region, disappears. And then finally, your liquid comes all the way over here, touches the two-phase region, so we have common tangent, again, in between here. I need to have those slopes be the same when we're in that two-phase region. But then, you see, I'm the lowest curve here in the pure phase. Everyone else is way above and disappeared. Great. Let's do another one. I am going to skip the... what is the concept of a common tangent and the thermodynamic variable? So remember, a common tangent is basically saying dg, dx in different phases are equal, and that is equal to your chemical potential. So remember, common tangent, to have equilibrium, we need chemical potentials to be equal, so that's the key there. All right, I think we all know how to draw the phases at this point, but you're still having to fill out those sections. But let's look at invariant points. So here, liquid to two-phase, eutectic. Eutectic here. Let's look at all the eutectics. There's going to be eutectic here, and that is pretty much it. Now let's go through here. All right, it's a congruent melting point right here, congruent melting point here, congruent melting point here, and a congruent melting point right here. All right, so let's look for, this is a peritectic, because liquid plus solid to new solid. So that's good. Liquid plus solid to new solid, that's another peritectic here. This is a single solid phase to a single solid phase here, and it goes to a liquid plus a, but it's the same solid phase there, so that doesn't count. So forget about that one, that's not an invariant point. This will be peritectic, solid, liquid to new solid. This will be a peritectoid, solid plus solid to new solid. And that is it. That's all she wrote. There we go. Excellent. All right. Composition of 60 CE. So CE 60 at what temperature do we have? 400 C. So at 400 C, we look like this. And again, similarly, we're in a two-phase region, so my degree of freedom is 1, just like we did last time. I have a composition in ALCE. I have a composition in, I'm just going to call this the beta. So my composition ALCE is approximately 0.5. My C naught is equal to 0.6. And my CB beta, I'm just going to call that 75. So if I want the fraction in beta, for example, I'm going to run away. So I'm going to do 0.6 minus 0.5 over 0.75 minus 0.5. And if I want the concentration, or the fraction, excuse me, of ALCE, I am going to run the opposite direction. So 0.75 minus 0.6 over 0.75 minus 0.5. And that makes sense because you see that this is going to be a slightly larger fraction because we're closer essentially to that side. Fantastic. Same relationship of the chemical potentials. All right. And then finally, 1,000 degrees. What is it? 1,010. So I'm going to do 1,100, excuse me. So very similar type of graph that we can kind of draw here. So you want to illustrate those two-phase regions. So remember, so we can draw here, and here's a two-phase, here and here's a two-phase, here and here's a two-phase, here and here's a two-phase. And so again, in each of those two-phase regions, you would basically draw through, and then you'd have each region come, touch, and come in, and then the next phase and the next phase. So just like we did on the previous problem. So good luck on your exam, and we'll see you next time. Thanks.